Come on in, everyone. Feel free to ask me any questions while we're waiting for everybody else to show up. Yeah, let some more people in. More people coming in. Some more people. Good gosh. All right, so it's technically time for class to already start, but go ahead. Does anybody have any questions right now before we start? Essentially, we are done with chapter 2. One thing I wanted to do, I actually did in the afternoon class, so you can go to the video from this afternoon, my 12 o'clock class. I actually posted it in week 3 module for your class, and I called it acceleration signs and vectors. So the very opening point is a quick little blurb showing students how you can get a positive acceleration and it means something speeding up, and a negative acceleration and it means, or excuse me, a positive acceleration, it means something slowing down, and a negative acceleration when it means something speeding up. So it's just something that you need to be cognizant of, and that's just the way the equations work. So I definitely recommend you check that out. I'm not going to waste that time in class doing it. I'm just going to jump on into the chapter 3 material, which is vectors. So anybody have any questions before I get rolling? All right, so let me go ahead and get started. I'm going to share my screen with you guys. It's not quite done yet. Hold on. Now it's coming. Okay, maybe that'll work. All right, so I'm going to write down this definition real quick. So a scalar is just a number. I'm making a little bit of a stretch to make sure you understand the difference between a number that has units versus a number that doesn't have units. That's also the difference between a ratio and a rate. A ratio is basically a fraction with two numbers that having the same units, whereas a ratio is, or excuse me, whereas a rate is two numbers, one on the top and one on the bottom, having different units. So the numbers that actually have units are called denominate numbers. But I'll promise you that word never comes up really in physics. It's more a matter of stuff you learn in your mathematics classes and stuff like that. I'm a big fan of trivia in general, and Jeopardy type stuff. So it's always helpful to know things like that. The other concept that we're going with is the vector. And the vector, of course, starts with V, just like the scalar starts with S, and just like the scalar quantity speed starts with S, the vector quantity V, or excuse me, the vector quantity velocity also starts with V. So a vector is an object that has a magnitude, which we can sort of think of as its size, and a direction. Now, that's not the only rules for it, but just about anything you're going to run into that has a direction and a magnitude would probably qualify, at least in some senses, as a vector. So it's okay. I will tell you that generally speaking, a vector also has to have certain properties. Those properties are exactly the properties you recall from like high school algebra 1 and high school algebra 2, where, A plus parentheses B plus C has got to equal A plus B in parentheses plus C. That's the associative property. Another one's like A plus B is equal to B plus A. That's the commutative property of addition. That that is something that a vector has to have, and other rules like that are necessities. But as long as it has those, and the ability to be converted from one coordinate system to another through a very specific process, that's really the hallmark of the vector. Again, we don't have to know all those little details in the calculus-based physics class. We just have to know how to work with vectors, and that means you need to know how to add vectors and subtract vectors. You need to know what multiplication of a vector by a scalar means. You need to know what multiplication of a vector by a vector means. In fact, there's two different ways that can be done, neither of which is what you're expecting unless you're already familiar with it. That's more what you need to know right now than, rules about how it transforms from one coordinate system to another and stuff like that. Those are important for the deep philosophical meanings of vectors and to make sense of things like general relativity and special relativity and stuff like that. The main thing is right now we just need to think of vectors as things that have magnitude and direction. I'm going to start off with addition of vectors, and I'm going to take it in a realm that we already are familiar with. For instance, one-dimensional vectors. For starters, in handwriting, a vector V can be written like that, or some people take the time to write that. There's other ways as well. You'll find out you could write vector V is equal to 3 I hat. That's another way of writing a vector. It could be, and in fact, with this one, it technically would have to be in meters per second if I really was assuming V was a velocity. You could also have, for instance, A is a vector, and that could be like 2.00 meters per second in the J hat direction, plus 1.00 meters per second every second in the K hat direction. So those are all different ways to write vectors. You could also write, for instance, another way is the vector is, let's say 10.0 newtons at 53.13 degrees. That's another way of writing it. Notice all of these have something to express it as something other than a number. So if I just wrote the number 3, you'd know that's a scalar because it doesn't have any of these fancy marks. Notice my 3 by itself is next to an I hat. That's the type of vector. It's called a unit vector. Notice my 2, which also has the meters per second every second right next to it. Unlike what I did with the 3, it has a J next to it. That's another unit vector. And the 1.00 meters per second has a K next to it, which is another unit vector. In fact, the I hat vector, that's what we call it, a hat, I hat, because that looks like a little hat sitting on top of it. The I hat vector is a vector that's 1 unit long. And I mean 1 unit, not 1 meter, not 1 inch, not 1 mile, 1 whole number unit. So it's like a non-denominate number is its magnitude. Uh, and it points in the positive x direction. The J is a 1 unit long vector that points in the positive y hat, the positive y direction. And the K hat is a 1 unit long vector that points in the positive z direction. Those are all nice ways we can express it, and we're not going to talk about those right now. We're going to go to the more normal statement of a vector like I have written down on that last one, which is 10 newtons at 53.13 degrees. If I have something as plain as this to indicate direction, then what that indicates is this. You have an x-axis, a y-axis, and you could have, for instance, the v vector like that. And what that at 53.13 degrees means is this. In other words, you sweep out from the positive x-axis in a counterclockwise direction 53.13 degrees. If you sweep it out in the counterclockwise direction, then that's a positive 53.13 degree angle, and everybody agrees that that's what that is. If you just write the at symbol, or you say in the direction of 53.13 degrees. If you do anything with just 53.13 without specifying north or south or x-axis or y-axis or any of that kind of stuff, then everybody needs to understand that you're talking about this. Similarly, if you had a vector, let's say b, which equals, let's say, 14.14 at negative 45.00 degrees, okay, then that vector would look more like this. And since it's negative, that means it would be on a rotation in the clockwise direction from the positive x-axis. Okay, so that's what that means. Does that make sense to everyone? So the way we indicate it in handwriting is a little different from typeset. Like when your book does it, all your book has to do is make a V with a bold print or a boldface type. And then everybody says, oh, that's something special. Either it's a vocabulary word, for instance, that you guys need to look up or know the definition of, or if it's with a single symbol, you say, oh, that must be a vector or a matrix or something fancy like that. And that's exactly what we do. So in handwritten stuff, you can use any of those various symbols. In typeset, they normally use boldface, but they can also use boldface with the vector symbol, the arrow over it, or you can use the non-boldface with the arrow over it. All that works, okay? So as I argued, or as I told you, I am going to try to take what you already know about vectors in one dimension and get to a general conclusion about how vectors are added and are subtracted. Okay, so let's start off. I'm going to draw a coordinate system, not a huge one necessarily. I'll draw a coordinate system like this, and I'm going to say that this axis is my x-axis. And just to, show you the abstractness of this, I'm going to say x is measured in newtons, because that's really what you do when you're plotting a vector. If the vector is a velocity, you're in some kind of weird velocity space where the x-axis and the y-axis has units of meters per second. Or if it's in a force space like I'm doing now, then it has units of newtons. Okay, so let's think for a second. Let's imagine a vector. I'm going to try to draw a vector right here. And that vector is going to be vector A. And notice that each of these blocks is a single unit. So this is 5, 6, 7, 8. So I think you all can tell that my first vector points to the right and has a magnitude of 3 newtons. And I could write that as at 0.0 degrees, right? Now let's add another vector. And basically what you're going to imagine is, let's imagine the origin is a spot on the road in front of your home. So you can just imagine maybe if you walk out your front door across your yard or your apartment complex's yard and step into the concrete, which might be a parking lot or it might be a road. Maybe there's a nail that's been driven into the asphalt there or into the cement there. You could use that as your point and you could call that the coordinate origin. And then you'd say, okay, well, now that I'm standing right next to it and looking uh, are even standing right on that nail and looking to the right, I'm going to call that my positive x-axis, and the left would be my negative x-axis, right? So if you were to take a walk from that nail, uh, let's say 3 meters to the right, then this vector A would represent your walk or your displacement as well. Only you'd have to graph it in a distance space as opposed to force space. Because remember, I use the units as newtons here. If you actually walk, though, it might be better to call it a meter. Now, what we did do is if you did go to that origin and walk to the right 3 meters, then you just drew an arrow from where you started to where you ended up, and that was your displacement vector. So the A is going to act like a displacement vectors, and I'm telling you that displacement vector is a perfect example of the vectors that we'll be dealing with. So I'm going to use them to guide us to figure out how to add vectors, at least graphically, and then we can make arguments of how to do it algebraically. So let's say at the end of your 3 meter/3 Newton walk, you then take another walk of say 5 meters. Do I want five? No, let's say four. Yeah, we'll take another walk of 4 meters. This one I'll do in red just to keep it separate so you can see the difference. Again, I'm going perfectly horizontal, or attempting to, and that vector is going to be called B. And vector B is going to be 4.0 newtons, also at 0.0 degrees. These are modeled just like displacement vectors. So I'll say modeled like displacement vectors. So hopefully you recall from my discussion of displacement vectors, what is the net displacement for these two paths or these two walks that you took? Can anybody describe that displacement vector for me? Let me open up the chat in case somebody's typing it in. But you can certainly just blurt it out. That's what I'm shooting for. But if you don't have a speaker, then let me know. So I walked 3 meters to the right. You can pretend it's 3 newtons if you wanted. And then I walked 4 meters to the right. Uh, what is my displacement vector? Jennifer and Julio, is it Julio? I assume it's Julio, not Julio. But Jennifer and Julio both said 7 meters. And that's right. Or 7 newtons, depending on. That's exactly right. And do y'all agree that it's pointing to the right? Okay. So what I'm going to do is I'm going to use yet another color. I'll use purple. And this time I'm going to let that represent my resultant vector. Well, I don't know what happened there, but that was not cool. It just let me draw it and then erased it. Let me do it again. Whoa, Nelly. Okay. Now it won't even let me. There it is. Whew. Trying to get this thing just right. So I'm trying to draw them all in the exact same space to be accurate, but at the same time, I can't draw them all in the exact same space because then they would cover each other up and you couldn't see them. So I'm trying to do it this way. Now what I'm going to do is put my little vector head on this, and this is called R for resultant. So the sum of any number of vectors That went really badly. Of vectors is called hold on, another person came in. It's called the resultant vector.
Why would the resultant vector and the b vector be the same length on the graph?
Ah, that is a little misinterpretation of the diagram. That's a good question. It would not be. Uh, what what you need to see here is I distinctly tried to draw B starting at the end of A. So B doesn't go all the way back to the origin. It only starts at the end of A. Does that make sense? So yeah, B had a length of 4 and A had a length of 3. And I could say specifically that R vector is now equal to, obviously you can see that it's 7.0 newtons also at 0.0 degrees. Okay. You could also do more fanciful things, like you can make a coordinate system again, and this time instead of all being addition, you could still add them, but you could add them and not all be parallel. So let me show you another example of that. So that's that vector, or that's that matrix. Dang it, why can't I get words right? That is that particular coordinate axis. That's the word I'm going for. Okay, that looks pretty good. Now I'm going to call this my y-axis. This time we'll do it in meters so it's a little less confusing. And this is in meters as well. So if I take my first vector and I draw it as something that goes from the origin to 4 spaces, okay, that would be vector A. Now, if I add to that another vector, which again, I'm going to start it right at the head of A. So remember, this isn't going all the way back to the origin. So now I'm going to start another vector that goes all the way to here. Okay. Then that's another vector. And that vector will be B. And in this scenario, A is equal to 4.0 meters at 0 degrees, which I could also write just for the record so you'll get a little bit of a head start as 4.0 meters I hat. So that's another wonderful way of writing that. You can just write I hat, and then everybody says, oh, okay, you mean it went in the positive x direction. And then you'd say, okay, well, what about that B vector? Well, that B vector went 1, 2, 3, 4, 5, 6, 7, 8 units. So I'm going to say it's 8.0 meters at 0.0 degrees. Or I could say it's 8.0 meters I hat again. So that's another way of doing that. But now let's take a third vector and let's make this guy green. I'm going to call this vector C, and I'm going to start it right at the tail of, or excuse me, the head of B. And I'm going to draw it all the way from the head of B. I drew it in opposite order, by the way, just because it's easier to. I'm drawing it from the head of B to its end, which is right here. And that's going to be called vector C. Now you can see vector C went 1, 2, 3, 4, 5 units. So vector C is 5.0 meters at, now in this case, you're going to say it's not 0 degrees. In fact, it's 180 degrees, like that. But you could also call that negative 5.0 meters I hat. And the negative just says, oh, I'm going to go a distance of 5 from the origin, but I'm going to have to go in the negative direction. Okay. So the resultant for this guy would be a vector from the origin to the end of C. So like that. this is vector R, and R is equal to A plus B plus C. And in fact, I think you all can tell that it's 1, 2, 3, 4, 5, 6, 7.0 meters at 0.0 degrees, which is 7.0 meters I hat as well. Okay, so you see what you do when one of the vectors is in the opposite direction? It's sort of subtracting, right? Now, this is actually addition of vectors. I'm not doing subtraction of any vectors here at all. This is all addition of vectors. As you can see, R is equal to A plus B plus C. But what we can see in common here is I took the first vector, and in the first example, for instance, I took the first vector and it was 3 units long pointing to the right. So I stuck its tail at the origin and drew its head 3 vectors or 3 spaces to the right and put the head there. Then I took the second vector, which was 4 units long, and I put the tail of it at the head of the last vector. And then I walked off 4 units to the right to put the head of that vector. So in that first example with just those 2 vectors, the resultant pointed from the origin, which is where the vector started, to the end of the head of the last vector. So R is from origin to the head of the last vector. And remember, you can technically do it in any order. I told you that when I hinted that the rules of algebra that you know from high school algebra, A plus B is equal to B plus A, and parenthesis A plus B, close parenthesis, plus C is equal to A plus parenthesis B plus C, close parenthesis. That all tells us that we can do these in any order we want. And the simplicity of me drawing B first in that first example. Imagine if I stuck the tail of B at the origin and then drew B there. Obviously, B would go all the way up to the 4th line. And then I put A at the end of that. And then that would go all the way to the 7th line because it's an additional 3. And I'd still get the same result. Do y'all see that? So that's key, and that helps us too in figuring out stuff. What I just gleaned from all this is this little bullet point right here, which I had to write over a couple different lines. R is from the origin to the head of the last vector, and R, remember, is the word for the resultant. Now let's look. Is that consistent with what we did down here below in the actual second example? So I need to correct this just a little bit. I want to make sure that everybody sees that that vector did all the way go back to the origin. So did I take the first vector and put its tail at the origin, and then at the head of that vector put the tail of the second vector? And then since I had 3 vectors instead of 2, did I then put the tail of the third vector at the head of the second? And finally, did I draw a line from the origin to the head of the last to represent my resultant vector? Is that what I did in the second diagram? Yeah, so you see R is a vector from the origin to the head of the last vector. And I'll put added here just to remind you that we are talking about addition. So that must be our rule. Now that's our rule, and I did it for one dimension, but that makes perfect sense. Like the second one saying, what if you walk from that little spot in front of your house, you walk 4 meters, and then from that spot you walked an additional 8 meters in the same direction, i.e., to the right, which might be the eastern direction. And then when you got to the end of that second walk of 8 meters, you took a 5 meter walk in the opposite direction, right? Do you see that you would end up at the end of the C vector? Okay. So yes, the vector from the origin to the end of the last does in fact give us the resultant. And that's exactly what we're going to use to add vectors. Okay, so we've got an idea about how we're going to add them, any number of them, if they're head to tail, and that's what we're talking about here because I'm putting the tail of one vector either at the origin if it's the first vector or at the head of the previous vector, and I do that repeatedly for however many vectors there are. Once I've covered all the vectors and put them all down, then the resultant is just a vector from the origin to the head of the last. So with that in mind, let me draw another coordinate system. Let's draw this one right here. And let's draw this one right here. This is going to be the x-axis. And I'll say, just for consistency, I'll put it in meters again. But remember, it doesn't have to be. It's just a little easier to picture when it's in meters. It's a little harder to picture when it's in meters per second and stuff like that. So the first thing I want to do is I want to take vector A, and I'm going to imagine walking again from that same nail in your out in front of your house. I now have the origin is still there, okay? And we might even go a little further and say that this direction is not only the y direction, it's the northern direction. And we'll say that this direction is not only x, it's the e direction. This direction down here is south, and this direction over here is west. And in fact, from that, we can say north implies at 90.0 degrees. That sort of is right, but to be honest with you, when you're actually talking about coordinates, your north is 0. So I'll say consistent with mathematics and standard angles, but inconsistent with compass headings. So for instance, if I pull out my phone, you might notice that with your, well, one of the apps that often comes with your phone is a compass. So if I look on my compass as I'm doing right here on my phone, okay, I can see, for instance, that it calls 0 degrees north, east 90, south 180, so on and so forth. So really, north equals 0.0 degrees, east equals 90.0 degrees, south equals 180.0 degrees, and west is equal to 270.0 degrees. And in fact, north comes back to 360.0 degrees as well. And they continue like that. Like I could add another 360 to 90 to get 450. And I could add another 360 to 180 to get 520. And I could add another 360 to 270 to get what 650. something like that. So anyways, that all starts to repeat itself over and over and over again. So just keep that in mind when we start talking about north and south and east and west. If they say north, then that means 0 degrees, which means straight along the y-axis. If they say east, that means 90 degrees straight along the x-axis. Now, you're not required to use that, but if they tell you that, that's what they're going on the assumption of. But when you go to use it, is if you draw it and you actually put the east pointing in the y direction and the north pointing in the x direction, and then the west would be in the south, the negative y direction. That's okay because I will have the diagram that I could look at. So if you're turning in a test with that type of coordinate system, as long as I've got the diagram to look at, you're good to go. But that's not how multiple choice questions work. So you have to stick to it. There's other ways too. I'll show you in future examples. Are if you look at the world's greatest vector addition problem that's linked in your module, you'll see that there's things like 15 degrees north of west. And that literally means uh, if you went straight to the left, that would be west. But if you, instead of going straight to the left, you went up 15 degrees to the left, that would be 15 degrees north of west. So that's another thing they can use, which is very, very different from west of north. If I said 15 degrees west of north, then north would be straight up, and now I'd want to go to the left 15 degrees. So they literally differ by a huge amount north of west versus west of north. So you'll see with the examples that you have in your homework, the examples you have in the practice tests, and the examples on my videos, you'll see all the different ways you can specify vectors. All right. So now that we have that out of the way, I'm going to put a new vector A on here, and I'm going to assume the vector goes from the origin and it goes to the right 3, but it goes upward 4. Okay. So my vector A is going to be from the origin to that dot right there. And now I'm going to move it to make sure that dot works like it's supposed to. That looks pretty good. So that's my vector A. Now, I might specify that because I know some trigonometry and I know some special things. So I now know that A is in fact equal to a vector 5.00 meters, and it is at 53.13 degrees. Now, in terms of those fancy little I hats and J hats, again, I'm not covering that yet, but I'll just show you quickly how this could be written using that, and it makes life a lot easier. That would be 3.00 meters I hat plus 4.00 meters J hat. That's a way I could express A. Okay, so when I was telling you I want to go to the right 3 and up 4, that's a way you can imagine walking like you're doing your slope you did in high school algebra 1, which is wonderful. That's also a way to walk off a vector if you know its components. This 3 meters is called the x component of the vector A, and this 4 meters is called the y component of vector A. Okay. Now, what we found is that in order to add vectors, what I want to do is put the tail of the second vector at the head of the first. So what we technically have to do is draw another coordinate system at the head of the first vector, like that. You don't technically have to draw it, but if I've given it to you in terms of angles, it'd be really helpful. But as you can tell, that's also helpful just by putting it on graph paper, because you know the horizontal lines are parallel to the x-axis and the vertical lines are parallel to the y-axis. So what I might do is instead imagine a vector that goes up to and to the left 5. So I'll imagine a vector that goes up to and to the left 5. 1, 2, 3, 4, 5. So my next vector is going to go from the head of the last vector to that spot. Again, I'm going to try to make this right on the money as best I can. And now I'm going to say this is vector B. Okay. And actually, I was really hoping I could move that down a little bit. You can see that the B is not sitting right on the origin, but it was supposed to be. So we just sort of ignore that for right now. It still should be fairly accurate. That being said, my B vector is actually not that easy to do unless I write it the way with the I hats and J hats. But what I do know is that it is over a distance to the left of 1, 2, 3, 4, 5. So if I take 5 squared and I add to it the 2 that it goes up squared, I get 29. And then if I take the square root of that, that should be the actual magnitude. So I'm going to say the square root of 29 is 5.39. So I'm going to say this one is 5.39 meters. And now it's going to be at what I can do is, since the opposite side is 2 and the adjacent side is 5, I can just do the inverse tangent of 2 over 5. So I'm going to say tangent inverse 2 divided by 5 in parentheses. That gives me 21.80. So I'm going to say that's at 21.80. But notice that is measuring this little bitty angle here, which is not the standard position. Okay. So I would have to say something along the lines of 21.80 north of west. So I'll do it that way. So I'm going to call this 21.80 degrees N of, or excuse me, yes, N of W. Okay. Because notice the negative x-axis is pointing in the westward direction, and north is upward, and I had to deviate from the westward direction towards the north, and that evidently had to be by 21.80 based on trigonometry. So if I wanted to add those two vectors, our rule was the resultant is a vector from the origin to the head of the last vector added. So what that means is I'm going to make a resultant vector, which is purple, and I'm going to draw it from the origin to that point right there. And yes, I was cheating using my iPad software stuff. Now I'm going to zoom in on this so I can put the head of the vector. And this is R. Okay. Now, evidently, since I use the idea that each one of these little blocks is 1 meter, we've already established a scale for these, and that is this distance from here to here is equal to 1 meter, and this distance from here to here is equal to 1 meter. And that also means that this distance from here to here is equal to 1.414 meters, because it's the square root of 2 basically from Pythagorean theorem. And I should clean this up just a tad bit. Okay. So what we can do is basically measure that vector and then tell what its actual angle is, and I'll know the solution. So I'm going to take on, literally, I'm just taking, I have a vernier caliper here. I really wish I had a plastic ruler. I do not see one, so that's not ideal. Actually, I thought I had one laying here. Let me check real quick. No, it looks like I have nothing but metal rulers. Yeah. Okay. Well, this is close enough. So what I'm using is vernier caliper, and I'm pretending it's not like a vernier caliper or anything. I'm just going to use the little stick part of it and measure it. And what I see for starters is I need to measure the width and height of one little square on this iPad. Okay. And I just made sure I was set to the right size. So it looks to me like that really sucks. That's not a good scenario at all. All right, I think I'm going to use the metal ruler, despite the fact that a metal ruler is not the best thing to put against the edge of my computer screen. But luckily, the good people at Wish and Temu send me all sorts of good things for cheap. Of questionable goodness, that is, but most of them have been pretty good. So what I'm going to do is I'm going to lay this right here on my iPad, and it's going to just randomly put comments up there for some reason that I don't know why it's doing now. I don't know why that came up at all, and I don't know how to get rid of it. It literally just started there. Oof, got rid of it. Okay. So what I'm going to try to do is lay this down on here and find a measurement that I like, which is right about there. Okay, so my 10 is lined up. It looks like the width of a rectangle, of one of these rectangles on my graph paper. It looks like the width of that is right about 0.59. So that's 0.59 centimeters, which I'm going to write right here. And that's pretty close. I'm going to now measure the height and see if I can figure out the same thing with that. Oh, good. It flips on me when I go to do it that way. This is weird, but it looks like the height is more like 0.49. So that actually presents a problem because these aren't exactly square. That's a 4 and a 9, by the way, centimeters. So if I actually measure this thing, it looks like I'm going up from the origin at 0. And it looks like I made this one to be 3.46 maybe. So the length of R is about 3.46 centimeters from my rectangular measurements. So using my ruler, in other words, 3.46 centimeters. That's a bit of a problem because it's not the scale. So I actually have a different scale I'm supposed to be using and moving up than when I'm moving to the left. So what I think I'm going to do is I'm going to take my measurement up, which is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 marks upward. And I'm going to multiply that by 0.49. And that means my measurement upward is about 2.94 centimeters. And then I'm going to take my 2 to the left and multiply that by 0.59 because that's how wide the rectangle was. And that gives me 1.18. So now I'm going to take the 2.94, square it, plus the 1.18, square that, and that gives me 10.036. So the magnitude of the purple vector R, and that's a way we can write the magnitude. I put the vector symbol with absolute value bars on it. That's one way of writing it. Another way a lot of mathematicians and math books use is double bars like that. That's a magnitude. In physics, we're kind of a little bit lazy. We want to get stuff over with. So we just take the vector symbol off of it, and then that represents the magnitude. In this case, I got 10.036 centimeters was the magnitude. And now I need to recognize that that is somewhere between 0.49 and 0.59. So if I take the average of 0.49 and 0.59, I'll say 0.54. So if I multiply this by 0.54, that's converting it to the scale on the paper, which is the more important one. So I just because they're supposed to be square, I took the average of the two. I'm definitely putting error in here, but I'm going to get something really close, not too terribly bad. So I'm going to take that 10.036 and I'm going to multiply that by 0.54, and that's going to give me 5.42. It's actually 5.41944 meters on the scale that we're using. Okay, so that's the magnitude of it. And I also want not just the magnitude, but I want the actual angle that it's rotated through. I have a protractor, a kind of crappy protractor on this ruler I got from Temu. It looks like it goes 0 to 90, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So each of these must be 10 degrees. So if I put this here and that there, it looks like this one is coming just a bit shy of 20 degrees to the left of the y-axis. Maybe I'll say 18 degrees. So I'm going to say this little angle right here is theta, and I'll say theta is about 18 degrees. I really can't estimate it. I'm not even sure I'm that good at estimating it to the nearest whole number because the protractor I'm using, you can see it's only marked in intervals of 10 degrees. So I'm just going on a whim here to see how close we can get despite all this crap. So I found out that the results were R is supposed to equal 10.04, or excuse me, 5.4. Yeah, I should do it that way. I grabbed the wrong number. Sorry about that. It should be 5.42 meters at, now that's 18 degrees beyond 90. So I just have to add it to 90. So I'll say at 108.0 degrees. Again, that zero is completely made up. So I'll put an underbar over it, and I'll even say I guessed at the 8. But that's roughly what it should be. Now, because we were lucky enough to have actually written this out in terms of I hats and J hats, or at least we could have, remember what B was. Another example for B, for instance, is that B went up 2 units and it went to the left 1, 2, 3, 4, 5 units. So what I'm going to say is negative 5.00 meters I hat plus 2 meters up. That'd be 2.00 meters in the J hat direction. So algebraically, since I have them in I, J, and K notation, all I have to do is add like terms. So algebraic addition yields the following. A plus B is equal to, I'm going to take the 3.00 meters and add to it the negative 5.00 meters, and all that'll go in front of I hat because they're like terms. Plus, I'm going to add the 4.00 meters to the 2.00 meters because both of those are in the Y direction, so that's J hat. So I end up getting negative 2.00 meters I hat plus 6.00 meters J hat. And if you look at the box, you can see that I did in fact go up 6 meters, and I did in fact go to the left 2 meters. So it's right on the money. Okay. Now we want it, because I gave you the vectors in magnitude and direction notation, we really want to return it in that same type of way. So now I'm going to use the Pythagorean theorem and say this is also equal to the square root of negative 2.00 meters squared plus 6.00 meters squared at inverse tangent of, and this is where I'm going to say 2/6, like that. And that's from positive y-axis. In other words, I know I'm not finding the angle in the standard position like I wanted to. So basically, negative 2 squared is just 4, and 6 squared is 36. So I get 40, and then I take the square root of that, and that gives me 6.32 meters, which I'm off by a whole number there. That's not too good. I got 5.42 instead of 6.32. And now I'm going to say it's at, if I take the inverse tangent of 2/6, I think that's the same number we had. That gives me 18.4 degrees. So that's really close. I measured that angle to be 18 degrees. This measured it at 18.4 degrees, so that's not bad. Okay. So even with all the trials and tribulations that I did there, I got a pretty good result. Numerically, the number is supposed to be exactly 6.32 at 18.4 degrees. Or you could call that 108.4. I'll put it this way. Okay. So what I did graphically was I found that it was 5.42 meters long at 108 degrees. So even if the 6.42 is right, I got a difference of 6.32 minus 5.42. That gives me a difference of 0.9. And now I'm going to divide that by 6.32. And in fact, that's only 14% error. So this is 14.2% error in R, and I'll say 108.4 minus 108 flat is equal to 0.4, and divide that by 108.4, and that gives me 0.36% in the direction. Okay. Now, again, I would expect 14 is really high. That's not that good, but given all the crap I had to do with this, it wasn't that big a deal. But when you're doing it on graph paper or even just notebook paper, but you're using a protractor, a straight edge, a ruler, in other words, and an actual centimeter scale, and maybe using a thin lead mechanical pencil, you could expect to get within 5% or 10% at the most, way less than 14%. But do y'all see how you can add them graphically just by putting them head to tail, head to tail, head to tail, head to tail, and then you draw a single vector from the tail of the first to the head of the last? That makes sense? Now, what if they weren't given to you that way? Let's say now we're going to do it where we put them tail to tail. I think the best way for me to do this would be to steal this diagram over again. So I'm going to use this little tool that I have, this sort of lasso thing. And copy that. I'll put it paste right here. Okay. So what I do want to do though is I want to get rid of some stuff. I'm going to get rid of that. Whoa. And get rid of this. That. Okay. And I'm going to get rid of this. Now notice what happened is this blue vector went up 2 and over 5. So I'm going to do that same thing using a blue vector. I'm going to go up 2 and over 5. So that's 1, 2, 3, 4, 5. So I want to draw it to that dot right there. So now I'm going to draw a vector from here to that dot. I didn't quite hit it exactly like I wanted to, so I moved it a little bit to make sure it's straight. Now that looks pretty good. Now I can get rid of my B vector that I drew over here. So when the vectors, well, actually, let me fix this real quick. Let me fix this one too. That's pretty bad. Okay. So now my B vector is this little guy, and the two vectors are head to tail. So how do you deal with two vectors that are, excuse me, I said head to tail. How do you deal with two vectors when they're tail to tail? Well, we already have the answer drawn there, and I left it there for this reason. But what I want to do is I want to make it a little less prominent, and I want to come up with it on my own so we can show you exactly how we do it. So what I'm going to do is zoom in on it and make it sort of a dashed vector. There's a dash, there's a dash, something like that. That's roughly like what it is. What I'd like to do though, whoa, is now let's see if I can make a copy of that vector using my lasso tool. So what I'm going to imagine doing, that is definitely not what I wanted. I just wanted that itty bitty vector. What I'm going to imagine doing is drawing that same little B vector at the end of A, because I'm imagining taking that little B vector and sliding along A. Because remember, vectors have to have magnitude and direction. So as long as you don't change the magnitude and direction, R direction, then you probably can feel somewhat confident that you haven't altered the value of the vector at all. But if I do take and slide the B vector along the A, then I'll have the A vector head at the tail of the B vector, and therefore I already know how to add those vectors. So what I'm going to do is I'm going to imagine going up from this point right here, which remember this vector A went over 3 and up 4. So it should literally be right there, even though I didn't draw it there. But now I want to draw it to go up 2 and over 5, which would be right here. So now I'm going to use my special tool to draw the vector exactly the way I wanted it. There it is right there. And this represents B, but it's me redrawing B. So I'll put it in dashed lines like that. And maybe even do that same thing with the vector to make it a dotted line instead of a whole line. Okay. Now, also, we chose to do that with B, but we're actually allowed to do that with A if we want as well. So I'm going to draw A now. And remember, it went over 3 and up 4. 1, 2, 3, 4. So I think the end of that should be right there. And now I'm going to use my special iPad tool to draw that perfectly straight. And now I'll put the arrow on that. And that is another representation of A. So I could write it as a dotted A like that. And again, I could make it a dashed line as well by doing that. Okay. So what you see is if I wanted to put them tail to tail, then my R vector would in fact just be this guy from the origin to that spot. Now, it didn't take my change to the proper type of letters, so, or proper type of drawing. There you go. So it did that now. And you see that the magnitude or the actual resultant vector came out to be exactly what it was before. Okay. So our rule is if the vectors are tail to tail, well, let me write both rules. Adding vectors. Graphically. Head to tail. Take the first vector and place its tail at the origin. The tail of the second goes at the head of the first. Okay. Repeat for all other vectors to be added. The resultant is a vector from the origin to the tail of the last vector. Does that make sense to everyone? I did just two here. I did more in the previous one, but I think you got enough of an idea. You just keep drawing them over and over and over again. Now, what about if they're tail to tail? In this case, it's a little more complicated. So because you can only take two at a time, and then you can get the resultant of the first two, and then add the third, and then the resultant of the first three, and then add the fourth. So taking two vectors at a time, you put the tail of each at the origin. Oops. And then you slide one or both vectors along the other to form a parallelogram. So you can see the dashed lines along with the original red vector and blue vector actually make a parallelogram. Opposite sides are parallel. Okay, so taking two vectors at a time, you put the tail of each at the origin, and then you slide one or both vectors along the other to form a parallelogram. So what I mean by that is I slid B along A, and then I slid A along B, right? The resultant of those two is a vector from their common tail, which is usually the origin, to the opposite vertex of the parallelogram. Whoa. Okay. And then you repeat with that resultant and the next vector. Dot, dot, dot. So if we only had two, we'd be done after making the parallelogram. If we had three, we would make the parallelogram, get the resultant, forget about the first two, and then add another vector, putting the tail at the origin, complete a parallelogram with that, get another resultant. That would be the sum of the first three. And you keep doing that until all the vectors have been used up. Does that make sense? So that's how they are added graphically. I want to show you now, before I actually show you more of the nutty or the nuts and bolts of how to add vectors, or more of the nitty gritty about adding vectors. I wanted to give you one little hint on how you deal with subtracting vectors. And the hint is probably the thing that you thought was the least useful thing in pre-algebra and algebra 1 and algebra 2. In pre-algebra, algebra 1 and algebra 2, for instance, we learned that A minus B was defined to be A plus the opposite of B. And notice the 3 bars there instead of 2 that's normally comes on an equals. This is the definition of subtraction. Okay. So if we wanted to subtract 2 vectors, what we need to do is we take A minus B and say that's going to be equal to the sum of A and the opposite of B. Now, that gets us into multiplying scalars by vectors. If you multiply a scalar by a vector, there's sort of 4 options. One, the scalar can be bigger in magnitude than 1 or smaller in magnitude of 1. That's 2 different conditions. Okay. If the scalar is bigger than 1 in magnitude, then you're going to make the vector longer by whatever that number is. So if it was 3 units long and you multiplied it by 3, you're now going to have a 9-unit long vector. If it was 3 units long and you multiplied it by 0.333, you're now going to have a 1 unit long vector. So that's what happens when you multiply by a number smaller than 1. And the previous example is when you multiply by a number bigger than 1. Now, that's what happens, period, with the magnitudes. The other problem is you can multiply it by a positive number, in which case the direction does not change at all. And then finally, the fourth case is when you multiply it by a negative number, in which case the direction changes by 180 degrees. So that's how you multiply a scalar times a vector. You're going to first ascertain whether the scalar is bigger than 1 or smaller than 1. Of course, equal to 1 means you're not going to change the sign at all, the size at all. So that's pretty much irrelevant. But in general, if you multiply a vector by a number bigger than 1, it's going to get longer. If you multiply it by a number smaller than 1 in magnitude, it's going to get smaller. Then if the number is positive, you're not going to mess with the direction at all. But if the number is negative, you're going to flip the direction exactly 180 degrees. So now I can quickly show you that if I had this vector right here as A, and I had this vector right here as B, and I wanted to find out what is A minus B, then what I would do is I would find negative B, which means B multiplied by -1. So you're not going to change its size at all, but you are going to change its direction. So what I'm going to do is flip colors, and I'm going to say this is negative B, but that's in a formation that we're not familiar with. That's 2 vectors that are head to head. We've talked about head to tail and tail to tail, but not head to head. So I'm going to use that other rule that allows me to slide that vector along this vector. And what I ultimately get, in fact, is this vector was about what, a half, 1, 2, 3, and 3/4 plus a half. So 3 3/4 plus a half is about 4 1/4. So I'm going to draw this vector at 4 1/4. 1, 2, 3, 4 1/4, right about there. And that is the vector negative B. So now you can see negative B and A are head to tail.
Can I ask a question?
Yes.
Could I also slide the B down so that the tail is touching the head of A?
Yeah, absolutely. So yeah, you can move B as necessary or move A. So you not only can you move B a different way, like you just said, as long as you don't change its direction or its magnitude, that's fine. So I could also have said, okay, I'm going to go 4.5 units downward or 4.25 units downward, in which case I'd say, well, this is about 3/4. So then I go 3/4 plus 1 plus 2 plus 3. That's 3/4 plus 3. I still need another half. So I would say right about here, and that would be negative b. So what you get then, remember when vectors are head to tail, you draw from the tail of one to the head of the last. So what I would draw is, let's use the color black. No, let's use green. So a minus b is this vector. But you can also see from her question, it's this vector, which notice looks like it's exactly parallel to the other one and looks like it might be the same length. Does that make sense? So that's how you do it. It says move negative b as necessary or move a so that vectors a and negative b are head to tail or tail to tail, because we know how to deal with addition for both of those. Use rules for those configurations. Okay. Notice how that when we started with two vectors that were head to tail, and it wasn't very convenient. We had to move stuff. But if you start with two vectors like this, let's say that's A and that's B, then negative B is just like that. And you can say, oh, well, that must be A minus B. So notice it always ends at the head of the positive one. Always ends at the head of the positive vector. In other words, A plus B, the A is the positive vector. A minus B, the A is the positive vector. C minus A, the C is the positive vector. So on and so forth. So you notice when they're tail to tail, subtraction's easy, but when they're head to tail, addition's easy. So tail to tail subtraction is easy. Head to tail addition is easy. Okay. And that's it. I've given you a little bit of stuff to see. Of course, you've got those videos in this week's module as well. For instance, there's solving vector and projectile problems. There's quick subtracting vectors by drawing, adding vectors by drawing, a 4-vector addition problem. World's Greatest Vector Addition Problem. I definitely recommend you watching World's Greatest Vector Addition Problem, and that'll show you the nuts and bolts of how to add vectors and how to specify vectors when I'm given all the different ways you can express it. Because we can express it with just the at symbol to give us a direction. We can use a compass heading of 36 degrees, all that different stuff in different ways. So that will hopefully show you. And we've got a good way into chapter 3, and it's time for you guys to go. So y'all are, of course, free to go. I'll wait for the last person to exit in case anybody has any questions. But have a nice weekend, and hopefully I should be there Monday. No ifs, ands, or buts about it for those of you who have me in class. Uh, Hopefully I'll be completely well by then.
Thank you. Have a good night.
Okay, feel better.
You're welcome. Thank you.
Thank
Anybody have
you.
any questions? No questions? How about Diego? Do you have any questions? It's like Diego, we just might not be here. All right. Well, have a good one, everybody. Looks like you're not typing anything or anything, so.